C. So it's over here. Okay, right.
Yeah, so my first step was I factored x squared out of the denominator, got x squared times 2x plus 1.
Right. Okay. So
And then I got the a, b, c value.
So let's start this off then. Okay, so right, so star, I'll just let star be the given guy. All right, so equals, you're right. So yeah, the numerator, I won't copy the numerator. Over, you're right, you factor out the x squared, all right? So x squared, and then it's a 2x plus 1, all right? And I'm okay if you just, it's okay to peek the answer to make sure they got the factorization right.
Yeah, I usually do that.
Yeah, that's okay. It's okay to peek. Yeah. Okay, the point is to ultimately learn. All right. Okay, so then the partial fraction. So then I'll just kind of let's see. All right, I'll do this then. Equals, right? So you have now I have it. Now let me know if you do it differently, but I have it as a over x.
Yeah, I have it like that too.
Over x squared. Of course, you can switch the a and the b out there. Plus c, okay, over 2x plus 1. All right. Okay, and I'll put a big arrow there. All right, and then we multiply to get the basic equation. We multiply both sides by the LCD, which is the always the bottom of the original expression. All right, so we get the numerator, which I'll write out. The numerator is 9x squared plus 14x plus 6. Okay, that's the numerator. Because when you multiply a fraction by its own denominator, which is this guy here, equivalently, you get the numerator, equals a, and that's a matter of who's missing, all right? So when you multiply this fraction by all this, okay, one of these x's knocks out this guy, but another x survives, and then the 2x plus 1 survives. So so in terms of the other pieces we need here, we're asking what pieces in the bottom are missing from the LCD, and those are the pieces that don't get canceled out. Okay, plus, okay, we have the b. When you multiply by this, the x squared knocks out the x squared there. We still have the 2x plus 1. Plus c. This time the 2x plus 1s knock each other out. We have the x squared. Did you get this basic equation?
No, I got a times 2x squared plus x. Oh, wait, that's what that is. Never mind, right? That's the same thing as that.
So wait, sorry, what did you get again?
I got a, and then in the parentheses, 2x squared plus x. That's the same as that, right?
Right, that's equivalent. Although for the plugin method, because I think maybe a hybrid or just a plugin method might work here, but it might be easier if you keep things factored, because then it's easier to plug numbers.
Yeah, because then if you okay.
So what you said is not wrong. I mean, if you had to, let me write what I think you said. I'll do this in green.
Yeah, I think that's my mistake right there.
Oh, it's not a mistake.
I wasn't thinking about that.
Yeah, it's not a mistake. It's just that it might be easier to do it my way. But if you had this a times the quantity, 2x squared plus x, that's correct. You're not wrong. It's just that I think it might be easier if you keep it in factored form like this, so that it's easier to plug in.
Mm-hmm.
So you save yourself some heartache. Like if you want to plug in -1/2, that'll save you a lot of heartache. Yeah, and -1/2 is a good value. -1/2 is a good plug-in value, right? Because it makes these equal to 0.
Okay, so I was able to solve for b first, and I got 6, and then I just didn't know what to do after that because I couldn't find any other value that made the others 0.
Okay, so you plugged in plugged in x equals 0, right? You plugged in x equals 0.
Yeah.
Right, and you worked it out. Yeah, and I see, because you get 6 equals b. I see that. All right, yeah. Okay, so that's in the bank. All right. Although we don't have to rewrite it, because I think we can get which one's C also. If you plug in -1/2 carefully, though, you gotta be careful though. So I'll do this in purple. All right. So what if we try x equals -1/2, right? Did you try that?
I did not try that.
Oh, okay. I might recommend that, because notice that makes both this and this equal to 0. So I would recommend that. Let's do that. Let me show you what it looks like. Highly recommended. Now, it does make, like this piece, it makes kind of hard, though. Even the calculator, a lot of people would mess this up. But you get, I'll do this on another line. 9 times, okay, -1/2 all squared. You need those parens, right? Plus 14 times -1/2 plus 6. So even that constant thing over there is kind of stressful for people. equals. I'll put the equals over here. Equals. Now, fortunately, see, this piece here becomes 0, right? Because the 2x plus 1 becomes 0. Okay. Basically, you get 0 plus 0. We can ignore all that stuff, right? Okay. And then the only term that really matters on the right is plus c times, and then x is negative 1/2. Put that in parens, and that's squared. Okay. Do you have any questions about what I have here?
Yeah, my brain just didn't think that I could plug in a fraction for x. I don't know why. I never thought about that.
Well, one of the values of the pre-calc class is that it gets you from breaking the old habits. Because I know in your old school algebra classes, yeah, everything factored nicely over the integers, or it was prime.
Yeah.
Right. But no, part of the challenge, and also, I had one great A student who told me one time that his hardest section was 0.1 because he couldn't wrap his head around intervals of numbers, right? The fact that if you consider the interval between 3 and 4, right? Okay, that has 3.5, it has pi, right? Lots, all these fractions. And so just getting the idea of intervals of real numbers, right? The fact that you don't just have 3 and 4 at the endpoints, you might have 3.5 in the middle, or pi, irrational guys. You have infinitely many numbers in there, right? Anyway, that's my little speech on that. Let's continue with that. All right. Okay, so on the left, yeah, let's do a little bit of arithmetic. 9 times the square of negative 1/2 is
1/4.
Right? Okay, 14 times negative 1/2. Basically, you're dividing 14 by -2, so you get
-7.
-7, right? Okay, it's good to sharpen that computational skill in your head. -7 plus 6, right? Equals. Okay, what's the square of negative 1/2?
1/4.
Right, we did that there, right? 1/4, and then c. Okay, do you agree with what I have here?
Yeah.
Okay, so let's continue. It's a worthwhile exercise. So 9 times, it's 9 over 1 times a quarter. Some people benefit from that. That's 9/4, right? Okay, and you can think of these as like poker chips. We can take away this, we can do -7 plus 6. That's a -1. Okay, imagine this plus a -7 plus a 6. You can add these chips in any order. The -7 and the 6, we got -1 equals 1/4 c. Okay, just kind of sharpening your computational skill. All right. Okay, just kind of quickly, I'll just write a little note here. 1 is how many fourths? 1 is
4/4.
4/4. What is 9/4 minus 4/4?
5/4.
5/4, right. So a lot of people need to have that voice in their head reminding themselves 5/4 equals 1/4 c. And hey, what can we do to both sides? We can multiply both sides by what?
4.
4. That's a great idea, right? So you don't even have to show it, but let me
Yeah.
people in the audience might benefit from this. All right. Okay. So again, that's 4 over 1, right? Basically, these die out, right? I guess we should put ones there. 5 equals, and that's the plain. So C is 5, right?
Yeah.
Okay. So we have that now. All right. Any questions so far? What I'm thinking is that since we've done 2 from the plugin method, we may as well do the third. We may as well plug in a third value for x. Some people like to switch to the algebra, but if you've gotten down 2, you just have one more, then maybe another plugin would be okay.
Okay, so now you have to find a value that would make B and C 0, right?
Well, no. See, the thing is, we've see 0 and -1/2 are the only clear values of x that'll knock out terms. So instead, give me a nice number we haven't plugged in yet.
Like 2.
2. How about 1?
Oh, okay. So then you plug in the A and B values, and then you just plug in a random x value, and then you find C.
Right. That's the idea.
Okay.
The idea that we know what A and we know what B and C are. Plug those in. So here's the thing. Remember, we have 2 general methods, right? We have the plugin method, and then going to the algebra distributing. But at this point, we've gotten 2 of the 3 already. Some people love algebra and they want to go to the algebra. That's fine. But I figure, why not take a nice number like 1, let's say, plug that in. I think we'll be okay. So let's do that. Let me grab another whiteboard. All right, let's do this in red. We haven't used that yet, red. Okay, unless it's triggering. Now it might be, it might be a good idea to rewrite the basic equation, just so that we don't forget ourselves, right? Okay, so you're kind of hinting at that, right? So we have, I'll rewrite the basic equation: 9x squared plus 14. Of course, you can plug in the 1 now, but 9x squared plus 14x plus 6 equals, we found that A we still have to find, right? A we still have to find, right? So A, I'll keep this factored. Although at this point that would have been fine too, but I'm assuming it's in factored form right now. Okay, ax 2x plus 1, all right. Plus we have the 6 now, right? And then 2x plus 1. We know b is 6, and we got c is 5, right? C is 5 from there. Plus c x squared. All right. Actually, either way might be fine. Doing either the algebra or plugging in x equals 1. In fact, I'll let you choose. Which do you think sounds better for you?
Just plug in is fine.
Plug in.
Yeah.
I think so too. Yeah, but some people
I like using that more.
Right. Okay, so x equals 1. Right. Oh, that must have been my algebra is better than my arithmetic. My arithmetic's pretty bad, so it depends on my mood, I guess. All right, so over here, now if you know how 1 works, right? 9. Yeah, the power, any power of 1 is 1, basically, right? So you're gonna get 9 plus 14 plus 6. Let's make it fast. Okay, so plug in 1 for x, we get 9 plus 14 plus 6, right? Equals. Okay, so we have x is 1. Okay, and then 2 plus 1 is 3. You don't have to explicitly plug in x equals 1, but show me some work. I believe you if you say that's 3. That's fine. Plus 6, 2 plus 1 is 3. All right, plus, I forgot, c was 5. I forgot to write that. C was 5. 5 times 1 squared, that's 1. Right, show some work, but yeah. You don't necessarily have to show me every arithmetic detail, but show some work. Okay, 14 and 6 is 20. Add 9 is 29, right? 29 equals, we get 3a plus, and then 18 plus 5 is 23. All right. Question so far?
No, I got it now. Thank you.
Okay, I'll go ahead and complete this.
Yeah.
Just for people's benefit. Okay, so and then we have subtract 23 from both sides. We get 6 equals 3a. A is 2. Although, don't be afraid if a comes out to be a fraction, like 1/4. If you get something hideous, right, like 37 over 110 or something, you're probably wrong. But they don't have to be integer. But I believe almost all my parameters were integer, as it turned out. But don't be afraid of 1/2 or something. Anyway, a equals 2. No, we're not done yet. What do you have to do at the end? What do you have to do? Like with those variation problems.
Write the decomposition of it.
Right, with the values for A, B, and C. Right, it's just like with variation, 0.16, you got to plug in for a K. Likewise here, you got to plug in. I'll actually type that note here. Plug into the PFD, not PDF, PFD form to get the PFD. Okay, we're not done yet. Okay, so it's 2 over x. You don't have to rewrite the original. The PFD is this. 2 over x plus b was 6. 6 over x squared plus c was 5, right? 5 over 2x plus 1. Now, you can reorder the fractions, but the tops must match with the bottoms. So like you can have like 6 over x squared plus 2 over x, like you did a reordering of fractions. That's okay if the corresponding signs attach. So you can reorder the terms, reorder the fractions, but the tops have to match with the bottoms, right? Let me make sure this is correct. It's good to get my own answer. 2 over x plus 6 over x squared plus 5 over 2x plus 1. All right, good. We did it. We did it. Any questions?
Not on that one, but I have another question.
Okay.
It's on let me find it real quick. 7.1. Oh my gosh, my papers are all over the place.
No, I know that feeling. I have a little box with a bunch of papers and text.
7.14b. Like, is there a certain way to figure out how many solutions the system has, or is it just because there's 2 x values?
Oh, I'm looking at the answers. 7.1.
I just don't know if I missed it in the notes, but like I just didn't really understand how to find how many solutions that they have
Right, right.
for all the systems.
Yeah, I wanted people. I didn't require people to graph, but I wanted people to have a sense of what the graphs look like. Right. Okay. So, and this takes you way back to like what 1.8 when we talked about x as a function of y. Those things that pass the HLT, right? But not necessarily the VLT. Okay. So let me grab another one of these. All right. Because my idea was that I didn't think the graphical method was appropriate to pinpoint solutions, but to kind of guess at numbers of solutions, I thought that would be appropriate. Okay, so we're doing this one here, number four. Let's talk about number 4 in general. I'll use purple as my primary color. Okay, 4 here. Let's discuss this. All right. So the 7173 block number 4. Let's talk about this in general. Okay, so first of all, what are the graphs of the equation of the equations here in the usual xy plane? Do you remember how to graph x equals y squared?
Yeah, they're both parabolas.
Right, they're both parabolas, but they open sideways, right? So if you want to do so basically the answer in text is these are both parabolas. Okay, it's the one word answer. They're both parabolas, right? But we even though I didn't have you graph, it's good to get a sense of what these graphs look like. I'll use blue for my graphs. All right, so x equals y squared. That's a parabola opening which way? The positive direction.
Yeah, to the right.
Correct. Whoops. Opens to the right. You don't have to be an artist, but yeah, it's the idea of that, right? A parabola, vertex at the origin, but it opens to the right. That's x equals y squared, by the way. I'll write that here. All right. Now, how do you graph x equals, don't worry about the 4 right now. How do you graph x equals the opposite of y squared? That's a parabola opening how?
It opens to the left and it starts at the 4 on the x-axis.
Very good, very, very good. Okay, so I'm going to draw this in green. Okay, so first of all, x equals opposite of y, whoops. X equals opposite of y squared looks like that. But as you correctly observe, if you add 4 to the right side, you're adding 4 to all the x coordinates. You're moving to the right. Very good. Very, very good. A lot of people wouldn't have remembered that. I'll draw it like that. Okay, and then in green, x equals 4 minus y squared. Okay, you didn't have to graph or label anything like that, but do you agree that that's the sense of our graphs? In fact, I can even pull up Desmos and get a more accurate picture of this. It might be more reassuring than my scribbling. All right, so here's x equals, whoops, here's x equals y squared, right? And here's x equals 4 minus y squared, all right? And in fact, we want these two intersection points. All right. If you have a good memory, you might remember that this is an approximation for root 2. So if you have a good memory for these things, that's a helpful hint. Yeah. All right. Anyway, so how many solutions does the system have? Well, let's look at the nicer graph. How many intersection points do you see?
2.
2. Right. So just from having a basic sense of the graphs, the answer is 2. So if you graph even my super messy graphs, you should be able to see graphically that we should get 2 solutions. And by the way, they will be symmetric about the x-axis. So a student would have to be a very, very sloppy artist to not make these observations, right, based on graphs. Questions about those observations?
Yeah, do we have to like show a mini graph to show that we know that there's 2 solutions?
No. I mean, I would encourage people. I would encourage people. So yeah, the idea was I wanted this to be some motivation for people to graph, but I didn't want to have people rummaging through chapter 0 too stressfully. I think it's nice. I think as a student, if you're keeping a notebook for yourself for your calc class, right? I think it's nice to put a little note like this, right, for your education, right? So I think that's nice. But in terms of the homework, just recognizing that you have 2 intersection points, therefore you have 2 solutions. So 2, yeah, really, so far it's one word, right? It's like A is parabolas, B is 2. But as a student, for your notebook, you might want to indicate why.
Okay.
Because trust me, you're going to want to keep a pre-calc notebook for calculus. Maybe I should have mentioned that on day one.
Yeah, I've been keeping all my homeworks and stuff.
Very good. Very good. Yeah. Okay, and C, find the solution set. Were you able to work out the algebra?
I actually just stopped there. I didn't. I just left that question and just went to a different one.
Oh, okay.
Just because I wanted to know about that first, but I was going to do it later. I can email you about that if I have any questions.
Okay.
But
and bear in mind that let's say I give you an A through I problem. I know that happens sometimes. If you get stuck at like E, it's not necessarily the death penalty for the rest. It might be, but you might be able to pick off some pieces to help build your confidence as you go back. Now, actually, let me tell you something. So you can use the substitution method where substitute x with y squared. You basically set, if you have x equals this, x equals that, you can set these right-hand sides equal to each other. And the algebra is okay. It's not bad. But see, here's the benefit to B. See, the thing is, if you have a nonlinear system, there's some obligation to check your solutions. But there are a couple of reasons why that's not so necessary here. One is that we have x as a function of y. That tends to decrease your need to check. And also, you have a sense of the graphs, right? Certainly with Desmos, right? Well, on a final exam, people couldn't use Desmos, but at least from a rudimentary graph like this, you should be able to figure out that there are two solutions because two real solutions because there are two intersection points between the graphs. So part of the purpose of B was so that in part C, it wasn't so necessary for you to check your solutions.
Okay, yeah, I just did the 4C part. I got it.
You got it right.
Yeah. Okay.
Right. So you got the two ordered pairs. I mean, right, and the order doesn't matter. Well, okay, the order of the ordered pairs doesn't matter. Of course, the order of the x and y matters. So you need this order here, this order there. You're good.
Yeah, I got it.
Right, right. And by the way, notice here see this matches what we had over here, right? 2 comma,
Yeah.
right. That is root 2 over there basically, and then 2 comma negative root 2. Yeah.
Okay. And then I just have one more question. It's 8.1 number 4. I'm kind of all over the place. I've just been like skipping sections that I don't really understand.
Oh no,
I ask questions. So
oh no, when students ask questions, I mean, come on, this thing goes from chapter 7 through 10. So no, I'm sure there'll be sessions, especially down the line, when people go chapter 7, chapter 10, chapter 8. So don't worry about that. All right, so 8.1, right? What number? 8.1.
Yeah, number 4. Sorry.
Number 4. Okay.
Yeah, I just don't understand how do I modify this to make it so well, I forgot what it's called, but like you want to, is it a 1 in the top left and then a 0 in the bottom left?
Yeah, row echelon form. That's right.
Okay, yeah, that.
Okay,
I just don't know how to modify it.
Okay, let's discuss this then. Okay. All right, so let's see here. Okay, I'm going to mark this in. Let's go back to blue. Or how about maybe a dark turquoise? Okay, 4. All right. Okay, so this is 8.1 number 4. Let's go that way. Here. All right. Solve the system. Okay, so here's a given system, and let's go ahead and write the first augmented matrix. And by the way, you should write down the original augmented matrix.
Yeah.
Okay, so we have 3, -9, slash is optional, 57. All right, and then -5, 4, -18. Okay, and I like to remind myself that that the variables or unknowns are x sub 1 and x sub 2, just as a note to myself. All right. So first off, let's remember what the target is. It's like a trig identity. Let's remember what the target is. The target is to get 1s along the main diagonal on the coefficient side and 0s all below. The rest are wild cards. That's a wild card. These are also wild cards over here. Okay, so we want a very nice row echelon form here. 1s along the main diagonal, 0s all below. That's the only way that we can get a unique solution for a square system, if you can get an augmented matrix like this. Otherwise, you don't have one unique solution. All right, and this one should have one unique, or it could be none. Maybe they're none. Yeah. That's it. That's if you get like 0, 0, 1 or something like that. All right. Anyway, we want a 1 in the upper left. Now, if you recognize that these are all divisible by 3, right, that helps. By the way, quickly, here's a quick test for divisibility by 3. Let's say you have a positive integer. Okay. If the digits add up to a multiple of 3, then it's divisible by 3. That's a very nice arithmetic tip that I've used throughout my life. If you have a positive integer and the digits add up to a multiple of 3, the integer is divisible by 3. That's a good thing to know.
Okay, I never knew that. So yeah, that is divisible then.
By the way, it works for 9 also. If you have a positive integer and the sum of digits add up to a multiple of 9, then that integer is divisible by 9. So that's also a great trick.
Okay.
All right. That's helped me a lot actually with simplifying radicals. And okay, so I'm going to start. Okay, I'm not going to get too cutesy with the description of the steps. Hey, we're going to take this row, divide by 3. Okay, to be honest, that's I don't have to get fancier than that, right? I mean, just yeah.
Are you able to just divide any row or multiply any row by anything?
That's correct. Because take a look.
Oh, I didn't know that.
Yeah. Because, well, let me look at it this way. Okay, so let's say that you have an equation like this. Think about old school, your old school algebra class. If you had 2x.
Oh yeah, because it's equate. Duh. Oh my
6,
gosh.
right?
I just keep looking at it differently because it's a matrix.
Oh yeah, but one of the key leaps of faith is, can you extend your knowledge from the single equation cases to the systems cases where you have multiple equations? And here, yeah, you agree you can divide through by 2, right?
Uh-huh.
Yeah. So don't be afraid to apply the things that you did back when you were dealing with one equation, right?
Yeah.
Okay. Well, you see how, for example, you couldn't just add 1 to everything, right? You agree that if I made that, that doesn't work, right? So, so just by looking at one equation, don't be afraid of what we did back in chapter 0. Look at the templates, the old school examples, 1 plus 1, right? Look at your basic old school examples and ask, what can I do with this thing, right? Yes, we can divide through by 2, 3, any real number but 0, right?
Okay.
So don't forget.
That makes sense.
Yeah, don't forget to review the old school basics along the way, right? Factoring, right? Old school factoring helped a ton with the new factoring. All right. Anyway, so row equivalents, little tilde there. I'm not going to mark off for this, but these matrices are not equal, right? They're row equivalent. They represent equal systems.
Wait, and also, do we have to show when we like flip the rows if we need to?
Well, show that separate step, and I would encourage you to put like a double arrow, or it's good for you and me if I can see what you did.
Yeah. Okay.
And do separate the step. Every time you do a new ERO type, certainly you want to separate out the step, write the new matrix. So unfortunately, and I know it's a rude awakening for students, you do have to write lots of matrices in this chapter.
Yeah. It's making a lot of pages, which is because scanning the papers to turn in the homework is a pain in the ass. So
that's okay. That's why I have unlimited capacity on my Yahoo. My Yahoo account, right? And a typical problem would take at least like a side of a sheet. Yeah. Okay. Anyway, so we can go ahead and divide by 3 here. 3 divided by 3 is 1. It's good to have that little drummer boy in your head. -9 divided by 3 is -3. 57 divided by 3. You can use a basic calculator. That's 19, right? Okay. Because as far as your education goes, on a final exam, I allow scientific calculators. So that's just a measure of the kinds of things you're allowed to use on a test if you had a test. All right. Anyway, copy row 2, and there's a lot of recopying, right? A lot of copying. Yeah. And then if you're like me, you have a problem with mistranscribing. So okay, -5, 4, -18. It might be worth your while to take a moment and make sure you haven't miscopied or miswritten anything. A lot of this is typographical.
So on the top where you put a little arrow and put divided by -3,
3.
Would we? Oh yeah, divided by 3. Would we be able to do that, or do we have to write like row 1, R1 divided by 3? Like, would that be better?
No, the thing is, I know that formal textbooks do that, so I thought that it was proper for me to do that. And the thing is, by the time you get to linear algebra, I think they'll assume you know the stuff already. So no, just do something that's clear, right? Like what I did up there, I think is clear, right? Now, granted, if you have to do one of those replacement, the addition elimination thing, the hardest one, where you add a multiple of one row to another, I would encourage you to do a table, right? Where you have the row you're replacing, the multiple of that row you're using. So I think that table helps a lot. And then if you label things, then you're indicating your step.
Okay.
Yeah. So I would recommend showing work on that on that third hard to name row type, right? The replacement or addition elimination method. Now, if you're switching or reordering rows, if you put some arrows, some double-headed arrows in or something, that might be okay. If you're rescaling, what I showed you right here, I'm sure I could interpret. And by the way, we like the fact that we have a 1 in the upper left. So don't try not to touch that guy. You can use that row, but don't manipulate. Don't change that row permanently. Yeah.
Okay.
Okay. Unless you're doing like Gauss Jordan or something, but okay. Questions?
Am I able to guess the next step?
Well, give me your thought process about what you might do next.
I think you would take add 5 times row 1 to row 2.
Exactly. Right.
Okay.
Because what's the strategy? You want to make the -5 a what?
0.
Correct. Yeah, I agree with you perfectly. Right. Okay, so I'll do that in blue. Just get a different or purple, different color here. All right. So like what I said, here's a good way of expressing that third type of ERO, which you should show for your benefit and mine. So we have the old row 2. That's the row you're changing or replacing. Okay. That's -5, 4. You don't really need the slash, but -18. Yeah, slash -18. All right. As you said, you're going to add 5 times. Okay, add 5 times row 1. By the way, I don't like saying subtract. If that were a +5, then output add a -5 times row 1 here. If that were a +5 there. Remember, you're better at adding. I know I am. I'm a lot better at adding. So if you have to get a negative in there, do that as part of the rescaling. All right. So 5 times 1 is 5. Okay, don't rush this. I know you're thinking, I know arithmetic. Well, yeah, it's easy to make mechanical errors. I know I make mechanical errors all the time. 5 times -3 is -15. Okay, a calculator might help here. 5 times 19 is 95. Because the way I think of it, 20 times 5 is 100, and it's the previous one. So previous multiple of 5, 95. All right, and then we add. See, it's very easy. You're combining like terms. You're adding. And what's the point? We're getting the new row 2. Good to label that. -5 and 5. The whole point was to make that a 0. I'll put a little smiley face here. That's easy on the tablet. But we like the 0 there. That was the point. 4 and -15 is a -11. Okay. -18 and 95. That's like a 77. That makes me smile because then I don't think I'll necessarily have fractions. Don't be afraid of fractions, but I'm glad that's a multiple of 11.
Yeah.
Yeah. All right. Again, the point is to make that a 0. Now remember, now some students might say, well, can we turn that into a 1? That's premature. If you try to make that a 1, then how are you going to make that a 0? You'll mess that up. So remember, the goal is you generally want to attack, you want to fix things column by column. Get column 1 good, get column 2 good. If there are more columns, get each subsequent column good. So first, get the 1 and the 0 good first, and then get that 1 down there good later. If you tried to make the 1 there before the 0, that's premature.
Well, can you leave it as -11 because it's a multiple of 77?
Okay. Now here's the thing. I gave an instruction in class, and I might email people about this. So on the final exam, I typically tell people that if there is a unique solution, you got to get the matrix down to row echelon form, which means that you can't leave the -11 there.
Okay.
So I might, I should email people. You know what? I should make a note. I should probably email people tonight, actually. I'll make a quick note. Although it's just a matter of inserting a matrix if they, well, yeah, because I want to have the right to grade on that, because that's one way for me to grade the final stuff. I'd like to know if people know what row echelon form is. And here's a special type. So let's continue. Okay, I'll continue on. Okay, we're in turquoise. Okay. All right. So tilde for row equivalence. I'm not going to grade on the tilde, but yeah. Okay, we're going to copy the row 1. That was good. 1.
Wait, what is that? A tilde?
Oh, the tilde means row equivalence. It means that I'm writing down the next augmented matrix.
Okay.
Remember, these matrices are not equal because we have a different. See here, we have a different entry in the same position, right? We have a 3 here, we have a 1 here. The only time 2 matrices are equal is if you have the same numbers in the same positions, right?
Okay, so When I wrote it down, I wrote that the first matrix you divide the top row by 3 equals the next one. Is that incorrect?
So yeah, it is incorrect. Now,
Would I draw an arrow instead?
that's okay too. Now,
Okay.
I'm not going to take off points, but as a matter of form, I prefer the tilde because you're indicating row equivalence. What that means is that these two augmented matrices, which represent systems, these two augmented matrices represent equivalent systems. Why do we care about equivalent systems? They have the same solution set, right? For example, back in your old school algebra class, 2x equals 6, x equals 3. These are equivalent equations because they have the same solution set, namely this guy. The point is that we like this equation because the solution set is obvious, right? The point of the Gibbs process is that we want to get down to a system whose solution set is easy to find.
Okay.
Right.
So instead of an equal sign, we should use the tilde.
Yeah, tilde,
mark.
because remember, the matrices are not technically equivalent. They're sorry, they're not technically equal. They're not technically equal because equal matrices, you have to have basically this equals himself, right? You need to have the same numbers and the same positions, right? Basically, only this matrix is equal to himself, right? But these are row equivalent matrices because they represent equivalent systems. They have the same solution set. So for example, I'll give you an example. In fact, I'll show you in the original homework set. See, we want to solve the system, right? What does that mean? We want to find an ordered pair x1, x2 that will solve both equations, right? A point that is on both lines, all right? But here's the thing. If I switch the order of the two equations, is that going to change the intersection point?
No.
No, right? Because they're just in different colors or whatever, right? So that's the idea. It doesn't matter what order you reorder them in. They have the same solution set. They have the same intersection point, right? So even though when you switch rows, you're technically changing the matrix, it's an unequal matrix. They're row equivalent matrices because they represent the same system. They represent equivalent systems with the same solution set, the same intersection point.
Okay, that makes sense.
Right. So yeah, I'm glad that we're talking about that underlying philosophy of solving systems. It's not just a matter of moving numbers around you. Okay, so I was about to, I'm going to rewrite this new row equivalent matrix. That's why I have the tilde there, right? No point in writing an equal matrix, right? That's the same thing. It helps sometimes, but if you're writing an equal matrix, you're just copying the matrix. Okay, 1, -3, 19. Now, some students might go, hey, wait, I thought we multiplied by 5. Yeah, that was a temporary step, but you want to revert back to the original first row, right? Like the 1 there. Okay, so we did use row 1 and rudely multiplied it by 5, but that was a temporary thing. Okay, now we have the new row 2, right? That's your 0, -11, 77. All right. Which is a good shape, but remember, this was our target. What number do we want in the position that the -11 is in? What number goes there?
1.
1, right? The goal, you don't have to write this note, but the goal is to render this a 1. There's really only one way to do that.
Yeah, multiply it by, or divide it by -111.
-11, right, correct. Okay, now why don't I use row 1 to hit row 2? Why not add a multiple of row 1 to row 2? What's the problem with doing that? Aside from the fact that you get an ugly fraction like, -11/3 or something like that. What's the problem with doing that? Using row 1 to make that a 1. What's the problem? What else would change?
The 0.
The 0. You like that 0.
Yeah, I don't want to change that 0.
You've just wiped the kitchen floor. You don't want to make it all dirty. So you can't use the 1 to hit the 0. That's a bad idea. Yeah, because you like these guys.
Yeah.
Right. So really, there's only one thing. I remember you can't multiply by 0. You can't. Yeah. Well, you can't, no point in that anyway. But the only way, really, the only practical way to get a 1 there is to divide by -11 or multiply by -1/11, which is equivalent. Same thing. Right. Okay. So let's do that. And I'm really glad that that's a 77 over there. All right. So tilde. All right. Recopy the first row. Yeah. 1, -11, 19. Be careful. And what does the new row become? Keep the 0, right?
0, 1, and -7.
Correct. -7. Good, -7, right. Okay, so kind of double checking, and that's a -7. I could have easily gotten the wrong sign. And this is in row echelon form.
Yeah, so now you can solve, right?
Yeah, now we can write up the system and back substitute, right? And if you like Gauss-Jordan elimination, you can use the 1 now to hit the -3 because the 0 doesn't hurt the 1, right? So if some people like Gauss-Jordan elimination, you can go to reduced row echelon form or use the 1 to make that a 0. So if you like the compact nature of matrices, you might want to do that. If you like the compact nature of matrices and you hate letters. Like some people hate x1, x2. I don't blame them. What's your choice? Would you like me to do the Gauss-Jordan way or write the system back substitute?
The Gauss-Jordan way is fine.
We'll try it? Okay, yeah. Because I don't think I really showed this explicitly in class. Okay, so let's try Gauss-Jordan. And see if you like it. Right. Gauss-Jordan is just a special case of Gebs where we eliminate up, basically. And you don't have to deal with the letters again. All right, so Gauss-Jordan. Okay, so what do we do? Now, it's another replacement step. So this time, we have the... I normally do these in purple. Okay, so the old row 1 is 1, -3, 19. I want to add a multiple of row 2. What number times this row will help the 1 kill the -3?
3.
3. 3 times 0 is 0. 3 times 1 is 3. 3 times -7 is -21. Add down to get the new row 1. Now remember, we actually do like the 1 here. Okay, so 1 plus 0 is 1. We like the 1 there anyway. -3 plus 3 is 0. You're in Vegas. You win 19, but you lose 21. What's happened to you?
2. -2.
Lost 2. Yes, -2. All right. So that's our new row 1, and you're going to like our next matrix.
Okay. I see where this is going.
Yeah. So if you like numbers more than letters, and many math people do, if you like numbers more than letters, you might prefer Gauss-Jordan. All right. So you get the new row 1 is 1, 0, / -2. The new row 2, the old row 2 we keep is 0, 1, -7. In fact, I barely care that it's x1, x2 because I don't repeat these unknowns again. We don't write these unknowns in the final answer. What's the solution? What's the solution as an ordered pair?
-2, 7.
Careful, -2.
Oh, -7.
Yeah, don't flip your sign there, right? You have the right order. Yeah, you read down because x1 is -2, x2 is -7. You don't have to do that reverse order thing from Gebs, right? But the braces, and voila. Right. And if you really want to, you can check, or you can check my answers. I have the answer, but on a final exam, people could check anyway. Yeah, that's one bad thing about having the answer. There is a satisfaction at checking by yourself.
Do you want us to back substitute to make sure?
If you do Gauss-Jordan, you don't have to.
Okay.
Yeah, because write the system. X1 is -2, x2 is -7. That's a system, but it's right there. There's nothing to do, right? You just have to grab those coordinates.
Yeah.
Again, if this were a final exam, you could check that and you'd be happy because if you plug in -2 and -7, -6 plus 63, that's 57. 10 minus 28, that's -18. Makes you feel really good. Yeah. And what point is this? If I graph these as lines in the x1, x2 plane, what's the significance of this point? It's the 3x minus.
It's the intersection point.
Yep. Let me see if I can. I'll do x and y here. 3x minus 9y equals 57. It's very gratifying when we see it graphically. -4x plus 4y equals -18. I'll probably have to. Oh, it's right here. Okay. And then -2, -7. Now remember, the world is not made up of just integers. Okay. I think there's a quote by Einstein: God created the integers, all else is the work of man. The Pythagoreans may have thought something like that. There you go. See, intersection point.
Okay.
Yeah. Although, like I said, I do recommend the graphing method as a method in the sense that you can't assume that everything's integer. But this does at least tell us that we have one solution and it's in quadrant 3. That might help. It's probably less work just to do it.
Yeah.
Yeah. Anyway, some comments here. Notice this is not only in row echelon form, it's in reduced row echelon form. MATLAB has a command for that. Reduced row echelon form, RREF, because that's a function of a matrix. If you have a matrix consisting of real numbers, there's only one reduced row echelon form for it, whereas there could be many row echelon forms. Okay,
Okay, that makes sense.
This process, when you go down to here and you take the coordinates, that's called Gauss-Jordan elimination, which is merely a special case of Gibbs. It's a special case of Gibbs where you also eliminate up and there's no back. And basically, the back substitution is done in matrix form. So when you do the row replacements upwards, making the ones down here, make these higher guys zeros, that sort of incorporates the back substitution for you. So everything's numerical.
Okay.
Yeah. So again, for people who love numbers, they can use Gauss-Jordan, go all the way, but make sure that you're accurate though, because if you make a mechanical error, see, one thing about Gibbs is that if you show me all the steps, I can give partial credit. Whereas with Gauss-Jordan, if you make an error, it's harder for me to give you partial credit.
Okay. And I think that's it. I don't really have any more questions.
We've clearly done a lot so far. Yeah.
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 I appreciate it. Thank you so much.
Oh, you're very welcome. Thank you for allowing me to record. I'm sure students will find this. In fact, I might want to email that tonight. That I'll have the video up here, a very illuminating video, and also reminding people that I do want them to take things to at least row echelon form if they have a square system with a unique solution.
Okay. Sorry, I can barely hear. My house is so loud right now.
Oh yeah. I was just saying I'm going to remind students tonight by email. Okay. So. Yeah, I remember iDogs too. Okay, so any other questions about either homework or just in general?
Okay, yeah, one more question.
Right.
I think I heard you say that 8.3 is optional.
Correct. 8.3 is optional. 8.5 is optional. I don't think I had any homework for 8.5 anyway. Did
Okay.
Wait, let me check.
Yeah, there was homework for 8.5.
Okay, so 8.3 is optional. See, I said these are all additional problems. Even my honor students.
Oh, I didn't even see that.
Yeah, okay. Yeah. And then 8, I don't think I had an 8.5.
Okay. Yeah, no.
No. I have to, but again,
yeah,
honor students have to do these. These are all additional problems. These are optional.
Okay.
Yeah,
I'll try to do them if I get the homework done in time.
Yeah, a Kramer's rule you might see once in a blue moon. There's some reference made to them, and also it's a neat idea that what's the purpose of finding determinants? Well, practical geometric purpose is that they help with errors in volumes. It actually turns out there's a relationship with errors in volumes. Like if you draw the vectors as position vectors and you consider the parallelograms or prisms that are constructed by those, you take the absolute value of the determinant, then that's the area or volume. That's a nice application. And that's used in Calc 3.